Hi everyone, I am from A-PHY team of TrueChip Solutions and welcome you all to this webinar. Today, we are going to present a webinar on MIPI A-PHY and MASS, that is MIPI Automotive SerDes Solutions. Our agenda of this webinar is to first discuss about the need for MASS. Then we will take an overview about what is MASS. After that, we will explain a use case where MASS is currently being used in the industry. Then we will go through the TrueChip solution of MASS. We will explain MIPI A-PHY, SerDes, A-PHY protocol adaptation layer, and MASS protocol layer. Finally, we will go through TrueChip A-PHY VIP features and deliverables. So let's start with why MASS is needed. Since the automotive industry is currently experiencing a rapid transformation in connectivity, automation, sharing, and electrification, collectively referred to as CASE. This transformation is basically can be seen in increasing adoption of ADAS, digital cockpits, IVI, and ADS. As a result, there is an increase in the demand of in-vehicle sensors such as cameras, lidar, and radar, as well as for higher camera and display resolutions and frame rates. So, the need to transmit huge data for interconnecting numerous vehicle sensors and display poses a design challenge for automobiles. So, there is a need for development of electrical and electronic architectures that basically capitalize on the latest high-speed automotive networking protocols. Also, the legacy MIPI solutions like C5 or D5 typically used in mobile systems are limited in terms of range. Hence, there is a requirement for a PHY solution designed specifically for automotive applications, which is more robust. This leads to the adoption of A-PHY in the context of MASS due to its attributes like it has longer range, higher reliability and resilience, and improved noise. Now let's see what is MASS. To overcome the challenges mentioned earlier and facilitate innovative architectures, the MIPI Alliance has introduced MIPI Automotive SerDes solutions. It basically facilitates the interconnection of cameras, sensors, and displays using various industry standard protocols like A-PHY, CSI2, DSI2, etc. It also integrates functional safety and security. As we know, before MASS, the automotive industry had to rely on proprietary SerDes protocols to establish long-range links. After MASS is composed of four key elements that are SerDes physical layer, high layer protocols, functional safety, and security. About these key elements, we will discuss in the upcoming slide. The MASS protocol basically contains A-PHY physical layer and link layer, protocol adaptation layer, and protocol layer. The protocol layer accommodates a wide variety of protocols, including CSI2, DSI2, EDP, DP, Ethernet, GPIO, SPI, and I2C. Their respective protocol adaptation layers are also present. Moving forward, the figure here shows MASS protocol stack in detail. As we can see from the slide, the topmost protocol layers are serviced with extensions like CSE and DSE for functional safety and security. The mentioned protocols we will discuss in the upcoming slides. Let's now see a use case of mass. As we can see from the slide, a rear mounted camera is aimed behind the vehicle that provides real-time video to a high-definition display, alerting the driver to objects in the car's path. The camera streams image data using CSI2 over A-PHY directly to an ECU. And after the ECU processes the data, it transmits a real-time video stream to a display on the driver's dashboard using either DSI2 or eDP-DP directly over the A-PHY network. Moving forward, as a VIP providers, we have also created mass solution. It basically contains A-PHY VIP and VIPs of all the latest version protocol adaptation layers, as you can see mentioned in the table, along with VIPs of all their respectivity protocols. This is the block diagram that shows TrueChip solution for mass. It consists of A-PHY and PAL source, sync, monitors, and scoreboard. All components are configurable and can be turned off or on, depending upon the requirement. Native protocols are also connected to the PALs as shown in the figure. Let's discuss more about components of mass protocol stack. First, we will discuss about MIPI A-PHY SerDes. MIPI A-PHY SerDes is the first asymmetrical industry standard long-range SerDes physical layer interface. A-PHY is designed to meet the specific needs of the automotive industry and eliminates the need for proprietary PHYs and bridges, simplifying in vehicle communication network and reducing cost, weight, and development time. Apart from standardization, A-PHY introduces resiliency and reliability. It also simplifies the integration of cameras, sensors, and displays. A-PHY's main task is data exchange between cameras, displays, and their corresponding ECUs within the automotive system. This is basically done by establishing an asymmetric data link between data sources and sinks. The link is of high-speed unidirectional data, embedded bidirectional control data, and the optional power delivery, all within a single cable. There are some key attributes of A-PHY, which includes low latency of maximum 6 microsecond, data rates of up to 16 Gbps in A-PHY version 1.0 and 32 Gbps in version 1.1, range of up to 15 meter, allowing upper layer protocols like CSI2 and DSI2 to traverse an entire vehicle through a single physical link. High reliability due to ultra low packet error rate that is below 10 to the power minus 19. High resiliency due to exceptional immunity to EMI effects. It also supports for multiple cable types like coaxial and differential pairs. A-PHY physical layer accommodates numerous higher layer protocols through its generic data link layer and protocol adaptation layers. Moving forward, A-PHY defines two profiles and 5 gears to meet the performance, cost, and complexity requirements of a broad range of different applications. As we can see from the given table, gears range from 2 Gbps to 16 Gbps per lane downlink and reverse downlink. Profile 1 is basically used for straightforward and cost-effective implementations, prioritizing time to market. It employs NRG, 8-bit NB encoding and forms basis for both Gear 1 and Gear 2. In contrast, Profile 2 meets the demands of high performance applications. It is based on PAM encoding, delivering superior EMC immunity and a lower packet error rate. Profile 2 forms basis for gears G3, G4 and G5. There are two uplink gears also defined at 100 Mbps and 200 Mbps. Profile 2 employs retransmission across all its downlink, reverse downlink and uplink implementations. Now we will discuss some A-PHY architectures. As you can see in the slide, the given architecture is for profile 1, G1 and G2. It is based on retransmission bypass and 8-bit 10-bit physical coding sublayer. Given architecture is for profile 2, G1 and G2. It is based on retransmission for downlink and uplink and 8-bit 10-bit physical coding sublayer. No retraining is used with 8-bit NB here. This slide shows PAMX single lane architecture. For uplink communication, RTS requests are sent over the downlink and no ACKs are used. Also, no retraining is used with 8-bit NB here. For downlink communication, RTS requests and ACKs are sent over the uplink. Also, retrain SCMAX requests are sent over the uplink here. Moving forward, this slide shows G3 to G5 dual lane downlink architecture. For uplink communication, RTS requests are sent over the downlink and no ACKs are used. Also, no retraining is used with 8-bit NB here. For downlink communication, RTS requests are ACKs are sent over the uplink. Also, retrain SCMAX requests are sent over the uplink here. Moving forward, this slide shows G3 to G5 asymmetric Q-port architecture. For reverse downlink communication, retransmission requests are sent over the downlink and no ACKs are used. Also, no retraining is used with 8-bit NB here. And for the downlink communication, RTS requests and ACKs are sent over the uplink. And retrain SCMAX requests are sent over the uplink here. Moving to next slide. It shows the G3 to G5 symmetric Q-port architecture. For reverse downlink communication, RTS requests are sent and ACKs are sent over the uplink. Also, no retrain SCMAX requests are sent over the uplink here. And for the downlink communication, RTS requests and ACKs are sent over the uplink. And also for the retrain SCMAX requests are sent over the uplink here. Moving forward. Now let's discuss more about retransmission mechanism. An A-PHY profile 2 5-port employs a dynamically modulated, time-bounded, local retransmission mechanism. Now we will understand these terms. Dynamically modulated because when retransmitted packets are transmitted using PAMX, they utilize a more robust, error-resistant payload subconstellation compared to the original transmission. Time-bounded because retransmission attempts persist only within the constraints of the overall delay. And it is local because the RTS mechanism is confined to a single hop A-PHY, meaning that the link layer remains unaware of its operation. Also, RTS is functional for both the 8-bit NB PCS and PAMX PCS. A-PHY basically provides two retransmission services. These are fixed delay retransmission and minimum delay retransmission. In fixed delay retransmission, it basically aims to implement retransmission while minimizing variations in latency. And in minimum delay retransmission, it focuses on implementing retransmission while introducing minimal latency. Also, there are two types of retransmission requests. One is single retransmission request and retransmission gap request. In single retransmission request, the receiver requests the retransmission of a single A packet that is either arrived with a bad CRC32 or was missing and not yet recovered. In retransmission gap request, the receiver seeks the retransmission of a range of consecutive missing A packets. Moving to next slide. The A-PHY port operates in two modes, active and non-active. Each mode can have various states and a series of transitions between these states. But together they form the operation mode state machine. During non-active mode, the A-PHY port stops transmitting any data into the A-PHY channel or interconnect. And during active mode, the A-PHY port maintains a data communication link with its partner A-PHY port. Moving to next slide. These are the state machine. As you can see here, different operating modes and all the corresponding transitions are shown here. Moving to next slide. Now let's discuss about A-PHY data link layer. A-PHY data link layer serves as the link between the native protocol adaptation layer and the A-PHY physical layer. The interaction between the APDLL and the NPAL takes place through APPI. APPI is a bidirectional, asymmetric, parallel, digital, packet-based interface. The APDLL can establish connections with multiple NPAL using a single local function. Additionally, it can be linked to either a single A-PHY network function or multiple A-PHY network function. The native file translates incoming native protocol data streams into the A-PHY representation. Conversely, it performs the reverse translation from A-PHY representation to native protocol representation. The representation employed by the APDLL takes the form of packets known as A packets. The key responsibilities of A-PHY data link layer include the routing of A packets, scheduling of A packets. In the routing where multiple NPALs exist, the APDLL's local function handles the distribution of A packet to their respective adaptation layers. Similarly, if there are multiple A-PHY port, the multiport function of the APDLL is responsible for the routing and forwarding of all A packets. In the scheduling of A packets, the A packets are forwarded to the same A-PHY port. The network function is responsible for their scheduling. Moving to next slide. This is the A packet structure. As we can see from this slide, 5 related fields are shown in black color. They are the fields controlled by the phi port, like A header fields, phi1, phi2, phi3, and phi headers and CRC, and the tail CRC32. These are sent with zeros and is ignored on reception by the A-PHY data link layer. Moving to next slide. As we can see from the slide, this is the A packet description. The A packet header consists of 8 header bytes, payload, and CRC32 tail. All the subfields are also shown here. Moving further, this figure shows logical APPI interface. APPI is basically used to make a connection between the A-PHY link layer and higher protocol adaptation layers. It is generic and application independent. APPI has two independent symmetrical interfaces. That is data out path which basically describes the data flow from APDLL to NPAL, and data in path, which basically describes the data flow from NPAL to APDLL. Now MIPI-PALs bridge the gap between the higher layer protocols and the A-PHY. MASS incorporates multiple PAL specifications to simplify the integration of A-PHY with a variety of upper layer protocols. PALs basically map higher layer protocols to A-PHY's A-packet format, as we can see from the given slide. Now moving forward, PAL CSI2 has different tunneling modes for data transmission, that is, transparent mode, legacy mode, and mixed mode. PAL CSI2 and PAL Ethernet supports tunneling and unifying function, chunking function, and packing function with time stamping. PAL EDP-DP can work in both EDP-DP, SDP, and EDP-DP aux over the A-PHY network. PAL GPIO supports oversampling mode and event pattern mode. PAL I2C supports single byte and multi-byte payload format and multi-session ICA modes. Now moving further. Now let's go through MASS protocol layer. MASS basically capitalizes on a collection of widely adopted higher layer protocols. These protocols include CSI2 for cameras, DSI2 and EDP-DP for displays, and variety of control protocols including I2C, GPIO, Ethernet, and I3C. MIPI's camera interface serve as the bridge between cameras and high-speed sensors, linking them to application processor or image signal processor. These protocols deliver high-resolution imaging, rich color, and advanced imaging capabilities to a variety of products like smartphones, tablets, automobiles, drones, wearables, and much more. CSI2 comes with features designed specifically for modern vehicle imaging system, such as RAW24, Smart Region of Interest, Unified Serial Link, Always On Sentinel Conduit, RAW28 image capture. Furthermore, CSI2 is enhanced with camera service extensions for safety and security, as well as the camera command sets for higher layer control. Now moving to the next slide. The DSI2 caters to the demands of multiple in-vehicle displays, largely due to its high bandwidth physical link, data compression capabilities, and a flexible yet straightforward architecture. DSI2 has the capacity to handle over 6 gigapixels per second of uncompressed image content. It basically transport layer incorporates visually lossless compression of display payloads, where DCS ensures that each display receives data packets synchronized to its own refresh rate. The DSI2 protocol has been designed to incorporate features like enhanced link integrity, particularly relevant for safety applications, and SDCP to safeguard entertainment streams. Complementing the DSI2, we have display service extensions, which are basically enhance safety and security, and display command sets, which provide the framework for higher layer control, further augmenting the capabilities of DSI2 for automotive display system. Now moving to some next slide. Now let's look more into functional safety and security aspect of the MASS. CSE and DSE extends the capabilities of CSI2 and DSI2 protocols respectively. These extensions enable functional safety, security, and other advanced functionalities. CSE and DSE have been designed to fulfill functional safety requirements from ASIL-B to ASIL-D within automotive systems. CSE introduces the enhanced safety and security for camera command interface. ESSCCI ESSCCI enables the protection of the control channel between a sensor and its associated ECU. This protection is achieved by tunneling the ESSCCI protocol over the A-PHY using the PAL I2C. On the other hand, DSE focuses on supporting HDCP for displays. HDCP ensures end-to-end content protection for DSI to display data. Additionally, it facilitates bridge-to-bridge data protection for eDP-DP display data. Both CSE and DSE define a service extension packet format, which serves data protection mechanism. In scenarios where an A-PHY bridge implementation is used, SCP packets are tunneled over C5 or D5 from the data source to an A-PHY SerDes bridge component. These SCP packets are then encapsulated into A-PHY A packets, which are transmitted over the packet switched A-PHY network to a receiver. Now the reverse process takes place at the far end receiver. If source sync components incorporate integrated A-PHY capabilities, SCP packets can be directly tunneled through the A-PHY network to a far end A-PHY receiver, eliminating the need for the bridge components. Within the A-PHY physical layer, various features are integrated to support functional safety for automotive systems. Like A-PHY's A-packet format incorporates CRCs in both the packet header and footer, an 8-bit message counter in the header to detect packet loss and replay attacks, and a timeout monitor to identify communication loss. A-PHY also implements a time-bound file-level local retransmission scheme known as retransmission for each A-PHY link. This scheme facilitates the recovery of damaged A packets to maintain a stable connection, and its operation is transparent to upper protocol layers. RTS basically provides remarkable resilience against EMI effects, and its low overhead contributes to A-PHY's high efficiency, particularly in upper gears G3, G4, and G5. Moving forward, now we will go through the TrueChip A-PHY VIP features. The TrueChip VIP provides a wide range of programmable protocol checks along with bus assertion for all protocol scenarios. Callback functionality is supported in all the components like source, sync, monitor, and scoreboard. VIP also provides bus and configuration coverage and also the assertion coverage, and achieves 100% in all the simulators. VIP supports use of randomization and constraints to generate corner scenarios. VIP also supports wide variety of static and dynamic error injection scenarios. It has support for dynamic configuration. Components can be reconfigured on the fly for each new packet. Summary is also provided of all the transactions received on bus along with real-time bus transaction details in log file. VIP also supports for TrueEye GUI for easy debugging like real-time transactions, latencies, statics, and many more in tabular and graphical format. We will discuss more about the TrueEye GUI in next slides. VIP can be easily integrated using Wrapper modules. Moving to next slide. There is message management, error or warning reporting can be controlled by changing their severity level or by suppressing it. Every error or warning having a unique error ID, and it will provide a detailed description of error, which is helpful in debugging. VIP also supports D port and Q port for both the profiles P1 and P2. Data lanes are configurable as single lane PAM or dual lane PAM. All the Q port operation modes are supported, like highly asymmetric, asymmetric, symmetric, Q fallback, highly asymmetric mode. All the gears are supported, like G1 to G5 for downlink and reverse downlink, and U1 U2 for uplink. VIP also supports ACMD and ACMP, and it also supports PAMX and NRZ 8B 10B modulation schemes. All the available PALs like CSI2, DSI2, EDPDP, Ethernet, GPIO, SPI, and I2C. VIP supports local functions, multi-port functions, and network functions. Moving forward to the next slide. Training parameters are configurable and support for dynamically configurable modes is available. Both the operation modes are supported, that are active and non-active. Also, mission mode and unidirectional mode is supported, that is basically used for the link training and initialization. Moving to next slide. TrueChip VIP comes with a TrueEye, that is basically the debugging tool. Now TrueEye helps in easy integration that will reduce man efforts and time. It helps in easy and effective debugging and searching, easy to detect and correct the errors, also easy to configure. It basically provides decoded packet, handshake, state machine, and command information for transaction level debug. It allows user to configure the VIP BFMs and create, modify, test in a graphical way, bypassing incorrect configs. We can search the required field, that is time, commands, errors, configs, etc. TrueEye provides information of errors with its probable causes. It reduces the man effort by giving user an option to automate the integration process and reduces the debug time up to 50% and speeds up the process. Engineers with lesser experience can successfully debug with ease based on useful info from TrueEye GUI. Bus utilization and idle time summary for performance of device can also be easily viewed on TrueEye GUI. Moving further, here we can see a table view for easy debugging. Table view is divided in two parts, transactions and transaction details. In transaction, there are multiple columns that will display all the transactions happened on the interface. On the top, we have search option in order to search any particular information or any other column value in the entire simulation. Transaction details will provide much more details for a selected transaction. From the GUI display, we can see A-PHY packet is formed at a time 501534,750 nanosecond. Expanding the drop down, we can see all the subfields of the A packets. Moving forward, here we can see the table view for PAL packet. Multiple columns display all the transaction happened in the interface. Here we can see SEP packet which has been formed in PAL and all its subfields in the drop-down list. This table view is one of the features in the easy debugging. There are a lot more features of TrueEye. you can contact us for a live demo. These are the TrueChip A-PHY VIP deliverables. All the VIP components, source, sync, monitor, and scoreboard are provided along with different type of test suites like directed, random, error injection, and dynamic test suites. In documentation, we provide integration guide for easy integration along with user manual and release notes. Thank you.